Welcome to the review of Lewis dot structures. We'll review small Lewis dot structures, and in class we'll work on applying the ideas to larger molecules than what we did in first year chemistry. When we drew a Lewis dot structure in first year chemistry, we used what's called the localized electron model. We didn't call it that, but basically we were looking at shared pairs and lone pairs of electrons. The shared pairs of electrons bound the atoms together using the atomic orbitals, and the lone pairs were localized on a particular atom. So the Lewis dot structure shows the valence electrons and how they're arranged amongst the atoms in the molecule, and the idea is to have a noble gas electron configuration for all the atoms. Remember the octet rule, we kind of want to have 8 valence electrons for most atoms. A quick review of the periodic table before we start drawing Lewis dot structures. Our main group elements, 1A through 8A, the S block and P block elements, have 1 through 8 valence electrons, except of course for helium, which has only 2 valence electrons. So the group number and the number of valence electrons are always the same for our main group elements. First, we're going to draw the Lewis dot structure for silicon tetrabromide, SiBr4. Let's count up the total number of valence electrons before we start to draw the Lewis dot structure. Silicon is in group 4A and has 4 valence electrons. Bromine is in group 7A and has 7 valence electrons. And there are 4 of those bromines, so times 4. Add those together, the sum is 32. We have 32 valence electrons to place in our Lewis dot structure. For these smaller molecules, we usually work off the idea of a central atom, and it's usually the less electronegative atom. When you look at a chemical formula, however, it's usually the atom where there's only one of them, in this case, the silicon. Place that in the center and draw shared pairs of electrons for each of the bromines. The dash means 2 electrons. We're going to draw electrons in pairs. Now we're going to make sure everything has its octet, has 8 electrons. Right now the silicon has access to 8 electrons. It's got 4 shared pairs. Each of the bromines are going to need some lone pairs to complete the octet. So each bromine gets 3 lone pairs and it has its octet. We have a total of 32 electrons in our Lewis dot structure. There are some exceptions to the octet rule. Not all atoms require 8 electrons. Some take less. So hydrogen from group 1A requires only 2 electrons. That's also referred to as the duet rule. Beryllium and magnesium, although they are metals, they are sometimes seen in molecules because of the higher electronegativities that they have for their group. And boron and aluminum, same kind of thing. Beryllium and magnesium only need 4 electrons instead of 8, and boron and aluminum need only 6 electrons. So we're going to draw the Lewis dot structure for BF3, boron trifluoride. Add up the total number of valence electrons. Boron is in group 3A and has 3 valence electrons. Fluorine is in group 7A and has 7 valence electrons. There are 3 of those, and so we add that up. That is 24 valence electrons. Boron will be our central atom. And boron now has access to 3 shared pairs, or 6 electrons, and so that is all it needs. Later on we will discuss why that is. But we can now give the fluorines their octets. Each fluorine gets 3 lone pairs, and if you add up all of the electrons, that adds up to 24 valence electrons. Some atoms will have more than 8 electrons. Third period and higher elements that have access to d orbitals is where you will typically see this happen, like phosphorus, sulfur, xenon, and chlorine, for example. So we've got sulfur hexafluoride here. Sulfur is in group 6A and has 6 valence electrons. Fluorine, again, is in group 7A and has 7 valence electrons. There are 6 of those fluorine atoms, and when you add them together, that adds up to 48 valence electrons for our Lewis dot structure. We're going to put sulfur in the center and then try to neatly arrange the fluorines, the 6 fluorines, around that sulfur. So you can see here that sulfur has access to 12 valence electrons, definitely an exception to the octet rule. Fluorines will still need their octets, however, and so we'll draw 3 lone pairs on each fluorine. So here's the completed Lewis dot structure. All fluorines now have their octet, and if you add up the electrons, it adds up to 48 valence electrons. Sometimes you may run into a situation where you've given everything its octet, but you still have extra electrons. And in that case, we will always put those on the central atom. In sulfur tetrafluoride, sulfur has 6 valence electrons. It's in group 6A. And fluorine has 7 valence electrons. It's in group 7A. There are 4 of those fluorines. That's 34 valence electrons. Sulfur goes in the center with the fluorines attached. And each fluorine needs its octet. It'll need 3 lone pairs. If you add up the number of valence electrons on this structure, however, there are only 32 electrons. We can have 34. So we will stick the extra pair on the central atom. And sulfur is now an exception to the octet rule. It has access to 10 valence electrons. Polyatomic ions are covalently bonded and made of nonmetals, but they overall carry a charge. So when we draw the Lewis dot structure, we have to take into account what the charge is. If the charge is negative, that means there are extra electrons, and we will add that number to our total number of valence electrons. If the polyatomic ion is positively charged, we're going to subtract the electrons that are equal to the charge from our total number. When we're done with our Lewis dot structure, we always draw brackets around that structure and indicate the charge. So, for example, we've got the sulfate polyatomic ion there. 6 valence electrons for the sulfur, 6 valence electrons for the oxygen times 4, and then that -2 charge means 2 extra electrons. Add that all together, that is 32 valence electrons. Sulfur goes in the center, and we're going to attach the oxygens. I also have given the oxygens their octet, and if you count them all up, we have 32 valence electrons. Draw a bracket around the sulfate polyatomic ion and indicate the charge. Sometimes atoms are going to share more than one pair of electrons. This is referred to as a multiple bond. So far we've been drawing single bonds. We can draw in double bonds where we share 2 pairs of electrons, or triple bonds where we share 3 pairs of electrons. The elements that are most commonly used for multiple bonding are carbon, oxygen, nitrogen, and sulfur, or cons. And what we're going to do is just draw a Lewis dot structure normally. When we're all done, we're going to double check the number of valence electrons. If we have too many in our structure, we know we need some multiple bonding. So for diatomic nitrogen, we have 10 valence electrons total, 5 times 2. We'll draw the Lewis dot structure as we would normally with a single bond and giving nitrogen, each nitrogen, its octet. If you add this up, though, this is 14 valence electrons. It's too many. We can only have 10. So we need to modify our structure. take a lone pair off of each atom. We can't have all these lone pairs. We need more shared pairs. So take a lone pair off of each atom and put a shared pair in instead. So 2 dashes means a double bond or 4 electrons. There are still 12 electrons though in the structure, and so we need to do this again. Take a lone pair off of each atom and put another shared pair in instead, and that's a triple bond. I'm just going to redraw this without all of the electrons crossed out. And the Lewis dot structure looks like this. So 6 electrons shared, or 3 pairs of electrons shared within the nitrogen molecule. I've got 10 electrons and everything still has its octet. For ozone, O3, I've got 18 electrons total, 6 times 3. And I'm going to draw this as a straight chain with the central atom. I'm not going to make a cyclic structure. So if I draw this normally with single bonds and give everything its octet, we get this. Notice I put the 2 lone pairs on the central atom to give its octet. If I count up the electrons, though, I have 20 electrons. And so I'm going to take a pair of electrons off the central atom, and then one of the 2 other atoms, I'm going to do this one, and then in between those 2 atoms, I'm going to put in a double bond. That is 18 electrons, and that is the Lewis dot structure. However, I could just as easily have put the double bond on the right side. And when this happens, this is called a resonance structure. So you could draw the Lewis dot structure for ozone one of 2 ways, with the double bond on the left side and with the double bond on the right side. There is no way to draw just a single structure for ozone, so we draw out both. And then in reality, what we think is that it's not a double bond and a single bond resonating back and forth between the 2 positions, that we actually end up with 2 bonds that are identical in energy and a single structure that's an average of these 2 structures. But this is how we represent it out, with the double-headed arrow in between the possible places to put the multiple bond. So finally for SO2, 6 valence electrons for sulfur and 6 valence electrons for oxygen times 2. That adds up to 18. Sulfur in the center with the oxygens attached. If all the atoms have their octet with lone pairs, we have 20 electrons, which is too many. So once again, we're going to remove a pair from the central atom and a pair from either of the oxygens, put in another shared pair instead. I just as easily could put that on the left side of the structure, and so I have resonance structures here, and I'm going to want to draw both. So here's my other resonance structure with the double bond on the left side.